for this yet another seminar. Well, great to see the numbers increasing there, people joining in. So we thought that during these last several months, several of you who have been joining us for the seminars, we're getting a bit tired of seeing old faces here all the time, every month. And so we thought of really starting mixing the young and the old. I'm included in the old, obviously. So in this month, given all the talent that we see in our groups and groups who are being associated with the GCC, we introduced this other format that we'll be using every other month, which is to have, instead of one longer seminar from a more established researcher, we would have two shorter seminars by some of the young guns out there from the GCC groups and others. So this month we'll have Tulio, Campos, and Shujaat, please correct me afterwards, to give the two shorter seminars as follows. So maybe I can go ahead and introduce briefly Tulio. So Tulio is a fairly young engineer who has finished his undergraduate studies in metallurgical engineering in 2018, only 2 years ago. And he is into his master's degree towards the end of it, under my supervision as well. He's one of the guys who I think would be also a good example to be involved in this group, because he's very excited about convolution. Already in his first year of his undergraduate degree, he already started working as an undergraduate researcher in my lab in Rio. So he's been quite a while there. If I'm not mistaken, 6 years now, already into undergrad and graduate studies. And so he, during that time, he published already 10 or 11 manuscripts in conferences and journals, and 3 already published and 2 in the process of being reviewed. So very enthusiastic, doing a lot of work. Tulio, today he's going to be talking about HPGR modeling, but he's been involved with a lot of things, including material characterization and including ball mill modeling using our mechanistic approaches. So without further ado, I'll really pass on for Tulio to give his presentation. So the format will be about 20 minutes for the presentations from Tulio and Shujaat, and followed by top 10 minutes of discussions, and then we'll go to the next presentation. Okay, please, Tulio, join the floor.
So thank you so much, Professor, for the introduction. I will share my screen. So, Professor, could you please confirm if everything is okay?
Yeah, it's perfect.
So, hello everyone. My name is Tulio and I'm a master's student at the Federal University of Rio de Janeiro. And today I'm going to show you some part of the work that we carried out regarding some advances in mathematical modeling of the PGR for pressing iron ore concentrates. And so that's the outline of my presentation. And after a brief introduction, I will show the 8PGR modeling overview, highlighting the key challenges that are not accounted by the previous modules. And after that, I will show the model development and also the model validation in different scales of operation. And finally, some industrial case studies highlighting how to use the model for industrial scale operations. So first, it's important to define what is the 8PGR, or the high pressure grinding hose. And this equipment has the size reduction based in interparticle breakage and basically operate with 2 counter-rotating rolls, the number 1 and 2 here in the figure, and the material is fed by the top of the equipment. And basically this roll number 1 has coupled a hydraulic system that allows the PGR to increase or decrease the applied pressure on the particle bed. And this floating row, this key feature of the 8PGR, ensures the equipment in a distinguished position inside comminution operations. For instance, the 8PGR has a high throughput, allows specific energy consumption, and also a high reduction ratio. And therefore, in the last 3 decades, some applications of the 8PGR in the minerals industry have been seen. And among these different applications, the one that was started in the middle of 1999 was the incorporation of the 8PGR inside some pelletizing plants. And here in Brazil, the company Vale was one of the pioneers applying the 8PGR inside an important step inside the iron ore pelletizing process. They call it pellet feed preparation step. And this step is quite important inside some pelletizing plants to improve the specific surface area of the iron ore concentrate, thus providing a more qualified product to the downstream operation. And here the PGR can operate in an integrated circuit with ball milling being applied even in the pre-grinding and also in the regrinding pre-pelletizing process. And of course, the application of the PGR here has some advantages. For instance, the improvement in the BSA, the specific surface area of the iron ore concentrate, in a process with high energy efficiency and also producing a very uniform product. And taking into account all of these advantages in the last 3 years, in a great partnership with the company Vale, we have tried to understand and to study the HPGR iron ore pellet feed from different points of view. Since trying to understand how different operating conditions can change the HPGR performance, also trying to understand how the particle breakage behavior for different iron ore concentrates that have been used to feed the HPGR can change the size reduction, and of course trying to apply the HPGR mathematical modeling in order to describe the HPGR performance from some variations in the feed characteristics and also in the operating conditions. And today I'm going to talk about of the work that we carried out regarding the application of the HPGR mathematical modeling for pressing iron ore concentrates. And among different models already proposed in the literature, these three presented here can be stated as the most popular models already available in the literature. And basically these three phenomenological approaches relies on the correlation between the material variables, the feed characteristics, or the key variables, the operating conditions, and also the machine settings to predict the HPGR performance from three different performance variables: the throughput, the power consumption, and also the product size distribution. And among these three models, the one that was proposed in 2009 by Torres and Casali relies on the plug flow model to describe the throughput using this equation presented above, and also relies on a correlation between the calculated nip angle and the compressive force applied to the particle bed to describe the power consumption using the equation presented here below. And finally, the particle breakage model proposed by Torres and Casali relies in a description based on the population balance model to describe the size reduction. And here the authors proposed to divide the row in different sections along the actual position, thus proposing a parabolic power profile along the row length. And the parabolic power profile can be defined by this equation presented here, thus providing us different breakage rates along the row length. And among all the models already used and available in the literature, the Torres and Casali model is the only one that allowed to describe the size reduction in different positions along the row length, thus providing us a finer product size distribution at the central region and also a coarser product size distribution at the edge region. And however, even though the Torres and Casali model have been used by different authors for Cooper ore operation and also applied as a model predictive control, there are some limitations and challenges regarding its application for pressing iron ore concentrates, as you can see here. So we have seen that the feed material ejected by the edge of the row and the material acceleration in the compression zone two challenges not accounted by the throughput model. Indeed, these limitations compromise the prediction of this performance variable. The comparison between experimental and calculated values have shown that the model underestimates the experimental measurements for both pilot scale and some industry scale HPGRs in a wide operating range. So indeed, this model is not a very good tool to describe the throughput for pressing iron ore concentrates. There are some other limitations regarding the feed characteristics and also some machine settings that are not accounted to calculate the NIP angle, thus compromising the description of the power consumption. And here the same trend presented for the throughput have been shown for the power consumption. The model underestimate the experimental measurements, highlighting that once again, this model is not a very good tool to describe the power consumption for both pilot scale HPGR and also for different industrial scale HPGRs presented here. And finally, the limitations for the particle breakage model. The first one is the most important limitation for different HPGR models. And here is important to bear in mind that there is no model in the literature that allowed to describe the particle breakage saturation effect. And the Torres and Casale model indeed overestimate the size reduction for iron ore concentrates when the HPGR is operating with high compressive force. In other words, high specific energy consumption. And there is an additional limitation for the Torres and Casale model regarding the variation in the pressure profile. As you can see, the Torres and Casale model relies on a constant shape profile, a parabolic profile, this red line presented here. But for industrial scale PGRs, we have seen that a more trapezoidal profile is the more proper description of this profile along the actual position instead of a parabolic profile. So highlighting that indeed this model has some limitations to describe the particle breakage behavior for pressing iron ore concentrates. And taking into account all of these limitations presented here, and in the last 3 years, we tried to improve the model prediction, basically using the main structure already proposed by Torres and Casale model, but including here some modifications that we have been tried to use. The first one, regarding the throughput model, this equation should be able to calculate the feed material ejected by the edge of the row, the proportion of material that will be ejected by the edge of the row, as you can see in the figure, according different operating conditions. The second modification relies on the properly description of the material acceleration in the compression zone. So this equation should be able to calculate the material speed according some variations in the operating conditions. And the last modification, just applying the new equation for the plug flow model, but here accounting for the two modifications that we proposed. For the power consumption model, we also proposed here some modifications, just a single fitting parameter in order to increase the calculated NIP angle and just trying to account for the different challenges that I presented before, and also trying to provide a more reliable description for the power consumption. And the last modifications proposed for the particle breakage model is 3 main modifications. The first one relies on the incorporation of the normalized breakage function in order to describe the particle breakage behavior for Brazilian iron ores in order to control the ultrafine particle generation. The second one relies on the incorporation of the breakage saturation effect, trying to apply this efficiency term here that will be able to change according to the application of the specific energy. And finally, a more general equation that should be able to describe the actual row profile. And this equation is based on the Fourier transform. And this single fitting parameter presented here should be able to change the shape profile from a more parabolic profile to a more trapezoidal profile. And of course, take into account all of the advantages presented here and the modifications that we presented for this model. We tried to validate the model in different scales of operation. And here, first, the comparison between experimental and calculated values for the throughput in some industrial scale with PGRs. As you can see, a very good agreement between experimental and calculated values for different equipments in a wide operating range, highlighting that indeed we have here a very good model with great fidelity to describe this performance variable in industrial scale operations. And we also validated this model for both pilot scaled PGR in a wide operating range here. So highlighting that the model indeed has a very good agreement between experimental and calculated measurements. And also for a lab scaled PGR, a very good description for different tests that we carried out, highlighting so that indeed this model is a very good tool to describe the throughput in different scales of operation, accounting for the modifications that we proposed. And for the power consumption model, we also validated the model, and here for a wide operating range for different equipments in industrial scale PGR, once again, we have been shown that the model is indeed a very good tool to describe the power consumption. And here is important to bear in mind that just a single fitting parameter was quite important to improve the model prediction. So in an industrial scale PGR, a very good agreement. Also in the pilot scale PGR for a wide operating range, a very good agreement for the calculating the experimental values. And finally for a lab scale PGR. And once again, the single fitting parameter used was quite impressive to improve the model prediction, highlighting the very good agreement between experimental and calculated values for different scales of operation. And here is important to bear in mind that the fitted parameter for each HPGR used was very close at each other, besides being used, although being used different equipments here to estimate the parameter. And finally, for the particle breakage model, first is important to estimate the optimal parameters that will describe the particle breakage behavior. And using this base case, here the comparison between experimental and fitted values, a very good agreement between both, highlighting so the optimal parameters on the right that will describe the normalized breakage function for different top size particles. So we used a constant breakage function and fitted different selection functions, specific selection functions for different equipments in industrial scale. So first for the validation, the prediction of the product BSCA for a pilot scale with PGR, as you can see, the single incorporation of the non-normalized breakage function for pressing iron ore concentrates in a pilot scale PGR was quite important to improve the model prediction. So we have here on the right the modifier Tosin-Casale model with a very good description of the product BSCA in a wide operating range, highlighting that indeed we have a very good model with great fidelity to describe this operation here. For industrial scale HPGRs, as you can see, the application of the modifier Tosin-Casale model with the non-normalized breakage function shown had great potential to describe the product BSCA, but indeed it's important to highlight here this test that were carried out with high specific compressive forces. And indeed, the Tosin-Casale model does not provide a very good description, since the absence of the proper description of the breakage saturation effect. And accounting for the modifications that we proposed here, once again, the comparison between calculated and experimental value is a more properly description of the size reduction, highlighting in a wide operating range for different equipment. So a very good agreement between experimental and calculated values. So highlighting that indeed we have here a very good model with great fidelity to describe this size reduction for industrial scale HPGRs. And the modified Tosin-Casale model was also validated in order to predict different shape profiles along the axial opposition. And this equation presented as our modification the single fitting parameter presented here should be able to change the shape profile from a more parabolic profile to a more trapezoidal profile. And using that trapezoidal profile, we tried to predict here the industrial scale operation, highlighting the very good agreement between experimental and calculated values for both BSA in the product and also the percent passing in 45 micrometers, and also highlighting the properly description of the shape profile using the trapezoidal profile instead of the parabolic profile. So indeed, after all the model validation, we have here a very good model, a robust model and practical model that can be used to describe the pressing iron ore concentrate for different scales of operation. And just in order to present here some results regarding the industrial case studies, I will present two case studies. The first one regarding the application for a pelletizing plant from Vale. And here the equipment that the HPGR that have been used by the company Vale is a quite impressive equipment with high roll dimensions. And there is a great problem in the operation that is the feeder does not ensure a shock fed condition during grinding. And therefore the HPGR, the real throughput of the HPGR is lower than the projected throughput. And so we proposed to the Vale team to apply a different circuit configuration here, a single stage pressing with recycle, applying that a product edge recycle, improving the mass of material inside the PGR, and maybe providing a more qualified product at the end of the operation. So using the model to simulate these different circuit configurations, first is important to highlight the very good agreement here in the base case, the single stage press in the traditional operation, experimental and simulated values. So the model has a good description of the operation, describing with great fidelity the different performance variables. And here presenting the different scenarios that we have been simulated. I will highlight here the single stage pressing with 40% of product edge recycle. And it's important to highlight that the throughput circuit was kept constant, but the specific energy was a little bit higher than the traditional operation, the single stage pressing. But the most important here is the product BSA that we archived here around 424 centimeters square per gram of the BSA increase from the feed in comparison to the single stage pressing 248 centimeters square per gram. So indeed, we have here a very good circuit configuration that allows to improve the blend specific surface area from the product, improve the qualification of the final product, and also increase the mass of material processed by the HPGR. And it's also important to highlight here the energy utilization used by both equipments was the same regarding here the single stage pressing and the single stage pressing with recycle, highlighting that indeed there is a great potential to apply the circuit configuration using the product edge recycle for pressing iron ore concentrates. And the second case study relies on the application of the model as a pseudo-dynamic model. And as you can see in a wide operating time, around 106 hours of operation, some minor variations in the roll velocity, but it's still important, and some great variations in the operating pressures during around 106 hours of operation. And applying the model to describe what is happening here, it's important to highlight that indeed the power consumption and the throughput have been depicted with great fidelity along the operation time. So a very good agreement between calculated and experimental values, highlighting that the model has great potential to be applied as a pseudo-dynamic model describing great variations in the operating conditions. And here the comparison between the size reduction, the product BSCA. And first, it's important to highlight that the model has here give us a response, a reliable response related to the variations of the operating condition, the operating pressure, highlighting that the model has some had a great sensitive to the variation of the operating pressure, but there are still limitations here to predict the product BSA, since we are using a constant feed size distribution, but there are still some variations in the feed size distribution that we are not accounting here, thus providing this great difference between the predicted and measured values for the product BSA. So the conclusions of my work, indeed, the modifications that we proposed that were quite important to improve the throughput and power consumption prediction, and also the particle breakage model validated in a wide operating range. The new equation was important to improve the description of the actual profile, and also the model was applied using 2 industrial case studies, highlighting that the model can be used to simulate different circuit configurations and improve the operation, and also to be applied as a pseudodynamic model, maybe using to improve the digitalization of the operation. And here the model shown indeed great potential to describe some industrial scale HPGR operation, and also some pilot scale and lab scale HPGR operation for pressing iron ore concentrates. So I would like to say thank you for the LTM team in the Federal University of Rio de Janeiro, and also thank you for the company Vale for the great partnership, and thank you all for your attention.
Okay, thanks Tulio for the presentation. So we have a few minutes now for questions. Tulio ran a bit over his time, but we still have time for that. But just in the meantime, just out of curiosity, you have seen in the first case study to show the picture of HPGR by ThyssenKrupp. It's a curiosity, but a lot of you know of the first attempt to use the HPGR in the minerals industry, in the hard rock industry. And that's exactly the same machine that was tried in 1995 in Cypress Cerrita in Arizona in the US, which was not a successful application of the HPGR pre-stud time. And this HPGR was pretty much decommissioned from that site, and then Vale ended up buying, and it's now, until today, pressing iron ore fines, just out of curiosity there. So I don't know if there's anybody already interested in putting some questions for Tulio.
Yeah, so this is Harry Lieberwald from Freiburg University. Thank you very much for the interesting presentation. I think there is a lot of interesting modeling behind. So for me, the point or the question was, when I was thinking about your and the key, as you mentioned again, is the pressure distribution over the width of the road. So how do you see it could be impacted with the new design of the roads? I mean, here we have the traditional design, but now the new designs, they have these border plates introduced by F. Smith, and that appears to be quite interesting and having quite interesting results and throughput of these mills. At least that is what also was confirmed by the guys from Krupp supplying this mill here. So I think there is some reason to think about these border plates seriously. How this would impact your calculation?
Okay, I'm sorry, Professor, could you please just repeat the question? I think that is a problem with the audio here.
Yeah, so maybe very short, Tulio, just what is your opinion about different alternatives to cheek plates, like the flanges and things like that, and how the model could cope with that?
Okay, yes, indeed, the cheek plates and the flange throws are two main technology used as the side seal for the HPGR, but I imagine that the flange throws could provide a more homogeneous pressure profile along the actual row position. And cheek plate is a very good side seal here, but indeed there is a great distinction between the pressure in the central region and also in the edge region. And I imagine that the cheek plate can provide a more homogeneous pressure profile along the actual position. And there are some other features in the HPGR operation, as the moisture content, for instance. We have seen that in a pilot scale HPGR, the feed moisture also can improve the pressure profile, providing a more homogeneous pressure profile along the row length instead of this great edge effect presented here.
Yeah, just complementing perhaps a colleague of Tulio's is actually doing the work on simulating in DEM in order to be able to capture this profile. So we're doing actually using DEM to capture the power profile or the pressure, which is, as Tulio mentioned, very much affected by the type of contention system that you have. Indeed, that's something on the way. Maybe next year, hopefully, we'll have an update on that. So Brian posed a question there. Is the work being done in iron ore also applicable for other ore type processing, such as nickel, gold?
Yes, so Brian, thank you for your question. Yes, we validated the model for pressing iron ore concentrates in different scales of operation as presented here, and for pressing iron ores in the tertiary crusher states using some data from Brazilian mines here for Anglo-American, but we need to try to apply the model for different materials as nickel, copper, and gold ore, for instance, but we still need to do that.
Another question from Francisco. He asks, is it possible to simulate different specific forces given a specific base case specific force? Do you think about the model on coarser comminution, such as replacement at tertiary crushing stage?
Yes, I think it's possible to apply different specific compressive force, just changing the operating pressure during grinding. And what is the second question, Professor?
So the second question, do you think the model could be applicable to predicting tertiary crushing, for instance?
Yes, as I said in the last question, indeed, we validated the model for pressing iron ore in the crusher states, tertiary crusher states, and the model shown at great fidelity to describe the size reduction, throughput, and power consumption. So it's possible to apply the model to these crusher states.
Okay, thanks, Tulio. I don't know, without going too much into Shujaat's time, and maybe we can actually thank Tulio for his presentation and move on to the next presentation. Thanks,
Okay,
Tulio, again.
Thank you.
Okay, so I'll pass on now to Malcolm to introduce Shujaat.
Right, Shujaat, can you get yourself on video and start sharing your screen while I introduce you? But
Yeah,
Shujaat demonstrated early determination by taking 2 years to get himself from applying to join a PhD with me to eventually getting through the door. It was at least 2 years through the university and Australian system. He's from Pakistan. He won the gold medal for his degree in mineral processing over the 4 years. And then he was awarded an Emerald Scholarship to go and study a master's in geosciences, which is at University of Liège, Nancy, Lullier. He also went to Freiburg. I wasn't sure if that was part of the degree, but for the 4 universities. So really got a good view around the European university scene before coming to join me and get promoted to making small rocks even smaller in a most precise manner, which he can share with you tonight, how we might be able to use that information. So Shujaat, over to you.
All right. Thank you very much, Malcolm, for such a nice introduction. And of course, it's my absolute pleasure to present my work today here. So I'll just share my screen with you now. Just give me. Could you please confirm if you can kindly see my screen?
Yep, that's good. It's all yours.
Sorry. So my PhD project is to develop a standardized methodology for the precise quantification of minimum comminution energy for industrial equipment calibration. And my advisors are Professor Malcolm Paul, Associate Professor Mohsen Yahyai, and Dr. Karina Barbusa. I'll straight jump on to comminution. As all of us know, since we are in the same domain, that comminution is considered a highly energy intensive process, and studies show that around 50 to 53% of the energy in the mining operations is consumed in comminution. Not only that, it is a highly energy inefficient process as well. Theoretical calculations based on free surface energy show that around 1% of the energy is actually used in the breakage. The rest is dissipated as heat, electromechanical losses, and all other sort of losses. But the question is, should we believe on this theoretical calculation of energy? Well, that has been encompassed into various controversial arguments. So, because there is always some unavoidable losses alongside actual breakage energy. So we need to consider that. So it would be even more pragmatic to say that the minimum comminution energy would be a better term for that. That basically includes some unavoidable losses as well. And until today, there is no standard baseline that can accurately measure the minimum comminution energy. To make comminution circuits energy efficient, there is a need for a method to measure practical minimum comminution energy. And if we are able to find a way to measure that energy, then we can basically measure the energy efficiency of a comminution circuit or a comminution equipment, and we can calibrate it against that method. Traditionally, around like 70 years ago, Bond developed a method to determine the comminution efficiency. And you can see the equation at the bottom here that he determines the comminution efficiency just by the ratio of bond ball mill work index and bond operating work index. So he sort of basically developed scaled down original ball mill, and that was empirical approach so that he could find out the behavior of breakage in that small mill. Then he defined the bond work index, as you can see through that equation presented on the screen. But that was entirely an empirical approach and was depending on the grinding environment. And operating work index, you can find it from the operating circuit. It can be calculated from the operating circuit or just by simply inverting the bond equation. And if bond work index value is exceeding, so it means it's a very hard rock, like greater than 20. If it's less, between 40 to 20, here in the table you can see. So this is for different type of ores. If it's soft, medium, hard, and very hard. So I would just highlight one point here, that if you look at the equation of bond work index, it basically relies on P80 and F80. That is the size at which 80% of the material passes in the feed and in the product. And this is an implicit assumption for the calculation, for the implementation of bond work equation, that the feed and product size distribution need to be parallel, as shown here in this graph. If not, then it will give you misleading results. So considering that Professor Malcolm Paul here at JKMRC coined the term of science-specific energy, that he defines as the energy consumed to generate a material below a marker size, such as 75 micron. It's believed that it is related to the generation of new surfaces. And as you see here in the graph, an approximation has been made that production of fine product uses over 90% of input energy. If you look here in this graph, and especially at the size below 0.1 or 0.75 micron, if your original energy is 20 kilowatt per hour, so around 90% of that energy will be consumed for producing material that would be fine or below 75 micron. And also a study by Musa and Morrison states that 70 to 80% of total surface area below 75 micron for AG, SAG, and ball mill circuits, as shown in that graph on the right. It is considered as a material property and is less dependent on the feed and product size distribution, as you can see in the graph in the bottom right. It is considered a more consistent hardness index opposed to other indices such as bond work index. And after all, it is independent of grinding environment unlike bond work index. We have a lot of breakage tests today. So they are either classified as bankable tests, geometallurgical tests, or proxy tests. And you can see here, if they're bankable, they could be like bond test, JK drop weight test, SMT test, similarly geomet test. I will not go into detail of these tests. However, I would highlight that they could be either bulk grindability test, or they could be either single particle breakage tests. So bulk grindability tests are not really well appreciated to be used for the characterization, because they don't give you the really right measure of the minimum practical combination energy, because there are always interparticle interactions. And there is a complexity of multiple breakage modes involved in that, such as compression, impact, and attrition altogether. And also it depends on the grinding environment. On the other hand, single particle breakage, a lot of studies since 1960s until now show that it is a very, accurate way, or quite appropriate way of establishing a relationship between input mechanical energy and size reduction. For instance, JK drop weight test was one of them, and also impact load cell, and then it has its own variants, such as silk. So I have put together here a summary of all different sort of characterization techniques altogether, so that kind of elucidates the comparison between all these techniques in terms of their capability of the particle size where all of these characterization techniques operate, and then their the amount of their capability to produce enough minus 75 micron material for the determination of size specific energy, the initial mass required for the test, and the time of the test. And here I'm comparing all these techniques using this trifecta system, with the green signal mean that it is highly acceptable, and the red signal means not desirable, and the yellow signal means acceptable or not acceptable depending on your needs. But as I said, I will not be going into the grindability testing details. That was just a comparative analysis. I will be more focusing on single particle breakage techniques. I will come towards the first one in the end. Before that, I will start from JK drop weight test and JK rotor breakage tester. So let's see the particle size where they operate. If we say that below around 12 millimeter, these techniques doesn't operate. So, but most of the energy is considered to be consumed in this area. So it is missing here. So it means, and also there is a lot of initial sample mass that is required for the test. So it is not very appropriate for both of these tests to use. Similarly, Sagmal test, again, it's missing in the fine range, and also initial sample mass is not very less. And if we go to Schoner device, then it doesn't have a capability to produce minus 75 micron, and likewise for short impact load cell, particle compression test, and so on and so on. So it doesn't produce any minus 75 micron. However, if we just go to the monolayer impact breakage test, that was basically a modified silk test performed by a student of Grant here at JKMRC like a couple of years back. It seems quite promising because it went all the way up to around 180 micron. However, and also it was able to collect sufficient amount of minus 75 micron, as you see here from a green signal, but it was very time consuming. Around 1 week was required for that. And also there are complexities involved with the experimental procedure. So putting them all together, what actually we needed was something like this: a method that can cover a wide range of particle sizes, that could give us sufficient 75 micron minus 75 micron material produced, that should consume very less mass, and that should be simple and quick. So that lays down my research motivation. So let's see, if we plot a graph between specific energy and person passing 75 micron. So the circles that you see here at the just close to the origin, they sort of relate to all the existing techniques because they were not able to generate enough minus 75 micron. So all the data lies here. And then they sort of extrapolate it as an assumption that everything is linear onward, but that is not actually the case, and it hasn't been proven scientifically yet, even for the method that was promising, the one that I was talking about. I mean, the one at the top here. And also there is always a sort of uncertainty associated here with these results, and that if you extrapolate, that will keep on increasing further. So it means like we need a technique that can sort of gives us a data that can determine the data in this missing range. And once we know that, then we will be able to compare or calibrate our industrial equipment or lab scale equipment with that minimum comminution energy, considering that. So yeah, we need single particle breakage test that can determine practical minimum comminution energy in terms of size specific energy. And the testing capability at fine size range down to 100 micron meter. Of course, if we are generating this data here, so we need to grind to a very fine and down to 100 micron and calibrate on-site comminution equipment. So that's my hypothesis as minimum. The first one is minimum achievable comminution energy can be used as a measure of ore competence to characterize ore bodies independent of comminution devices. Secondly, size-specific energy determined through particle monolayer breakage can be used as a reliable measure of minimum achievable comminution energy. And third, a precision Rolls crusher can be used as a practical characterization device to accurately measure the minimum achievable comminution energy across a wide range of initial particle sizes using particle monolayer breakage. The objectives of my thesis are to measure size-specific energy up to 80% passing minus 75 micrometer. Second one is to validate the precision Rolls crusher size-specific energy results. How will we validate that? To test by testing same samples other researchers used for monolayer impact breakage and single particle breakage tests, such as Raja is the one that I was talking about, the grant student, and Fatma Saidi, and they have their samples already here with us, and we will compare our results with them. Third, compare measure size specific energy to that calculated from high quality production plant surveys. So these are basically the surveys data, and we have samples from the surveys, so our results will be the results that will be made using Rolls crusher will be compared with them afterward. And fourth, simplify and streamline the testing methodology to suit commercial testing of ore variability. So the last step of that thesis would be to simplify the methodology so that it can be well suited for the commercial testing. What is precision Rolls crusher? So here is a sneak peek of that. So it is a device that is here at JKMRC since 2017, I guess. So here you see that we have a feeder, digital feeder, and we can adjust the gap of digital feeder so that we can allow a monolayer of feed to leave the feeder. And then we have a chute that drops right in the middle of counter-rotating rolls driven by two motors, and right in between two motors are highly precise torque sensors that are more obvious in the side view of this picture here. So, and once the material is passed through that, it is being broken and collected here at the collecting pan, and then we have an embedded 75 micron sieve here. Everything that is flown off inside the chamber of the crusher is screened out. Everything that is less than minus 75 micron will be collected by a domestic Dyson cleaner. So we actually do not want any minus 75 micron to be lost in the nowhere, in fact. So we are interested in real and accurate collection of minus 75 micron. And the rolls have diameter of 250 millimeter and width of 100 millimeter. And yeah, it's an open system. We can see through it, and it's tangible. Yeah. So this is a bit of the schematic diagram of precision Rolls crusher. So as I said, we are interested in minimum breakage energy determination. So the approach that we would be using is progressive breakage, so that we can sort of measure the primary breakage energy, like the minimum fracture energy that you see here inside that dotted box. So what we do first, first we set a gap right equivalent to the size of the particle, and we just break them, the monolayer of those particles, around 300 grams of the mass approximately. And then we collect the product, and then we recycle that product again through pass 2, and we further reduce the gap. So the reduction ratio between the particle size and the gap is kept around like minimum, so that it shouldn't either overcrush or under chip off the particles. So for now, we have done some test work, and for which we did 0.85 of the reduction ratio between initial particle size and the gap. Anyway, so coming back here, so we keep reducing the gap progressively, and we recycle the material. And every third pass, it could be every fourth pass, it could be every pass, although, but here we are doing it every third pass. We recycle the material again, and every third pass we measure the product's size distribution, and we remove the minus 75 micron material, and then rest of the product is again recycled. And breakage energy, calculation of breakage energy. So here is the energy equation. Since we said like we have highly sensitive torque transducers, that basically gives us the data of speed in RPMs and roll torque in Newton meter. So then we convert that angular speed and torque into energy using this equation as shown on your figures. So what we do basically, we run the equipment at no load for a while, and then we pour in the feed, so that we call it a breakage event. You see here the torque is changing, and then again, like we leave it running for a while at no load, and then we convert that data into energy using this equation here. So energy is here, but the beauty is that you see here very much like noisy data, but when you accumulate that data, you see a very the energy, and when you normalize it, you see like you have a no load starting at zero energy, and then it keeps increasing during the breakage event, and again once the breakage is finished, it becomes constant. And also we have the from the manufacturer the electrical energy measurement system installed inside. So but we do not take that into consideration, because motor power not used due to substantial losses and inefficiency of low speed and torque. Here are some results. As I said, we have done a bit of work on a couple of ores here, and I'm showing you a bit of results that what we got from that. So we basically went down to 500 micron meter or 0.5 millimeter gap in the earlier studies, and we tested 3 different sizes. So one is 1.4, the second is top size 2.8, and the third one was the natural BSD of the ore. So if we plot specific energy versus percent passing 75 micron, we see sort of very linear relationship for both the sizes, for 1.4 millimeter and 2.8. However, if we go for the natural BSD, you see in the beginning it's a bit kinky, but after a while then it starts going straight. And if we plot specific energy versus gap width for the same sizes, and so we see that if we sort of decrease the gap width, so as expected, the specific energy will increase, as you see here, if you go opposite, and vice versa. So the reason of trying different feeds was to investigate the influence of feed size distribution on size specific energy. And it's again for 1.4 top size, 2.8, and natural BSD. And then here is a graph between specific energy versus reduction ratio for all those 3 top sizes. And what we see that when we plot cumulative specific energy versus reduction ratio, sorry for the spelling mistake here. So reduction ratio is defined here as a particle top size divided by gap width. So what we see that it sort of increases linearly for the top size of 1.4 for different sort of ores. And then for the 2.8 size for ore E, it's sort of straight. However, for the rest of the ores, it's not really straight, it's following maybe a little bit trajectory and going ahead. And again, the trajectory is followed by all the 3 ores for the natural PhDs for the 3 different ores. And here is the progeny distribution over the progressive stages when we break it all the way from the top size to the down, and we see that we get really progressive breakage as we go down the way, all the way to 500 micron. And it's just for the 2 different ores, just to show that, yeah, it's giving us quite progressive and promising results. So contribution to knowledge is, it can provide a precise and practical measure of minimum communication energy at the fine sizes down to 100 micron meter, which hasn't been done by any of the existing technique as of now. And it has this, if this methodology has a potential to baseline, has a potential for the determination of communication equipment operating efficiency. And also communication, as we know that communication models require ore characterization spanning full feed and content of size distribution. And when we look at the existing breakage models, we see that the extrapolation to the fine sizes is highly inaccurate, and it sort of underestimates the energy consumption, because majority of the energy consumed in grinding the fine sizes. So we really need a method to fill the gap and get a right energy number at that fine size range. So yeah, that is it. Thank you very much for your attention.
Thank you, Shujaat. So came in close to time. Maybe we can have 5 minutes of questions. We won't be much after 9 then. As you can see, Shujaat's well launched in, but at the beginning stage of running the full process. You can ask him some really tough questions.
Yeah, Suja, perhaps I could ask you the first question, the first tough question. You always speak about the minimum combination energy. So yes. Can you hear me?
Yes, yes, I do.
So, but you only use compression. So how comes that you conclude that compression gives you the minimum conclusion energy? Why not share? If you just would change the speed, if you would come to the differential speed of your rollers, I could imagine you get complete different results for certain ores at least.
Yeah, so the thing is, during the scoping studies, I would be sort of finding that appropriate speed so that I don't find like any sort of slip between the particle that is falling in the middle of rolls. There shouldn't be any momentary slip. So the speed of rolls should actually match with the speed of the falling particle. Or I yet need to investigate that what is the appropriate speed that I should adjust to get it going to ensure the condition of minimum breakage.
I'm not focusing on this initial slippage, which you can never completely avoid with the setup. But I'm really thinking about share load. You speak about you stipulate your results as a minimum comminution energy.
Yes.
But this is only applicable for your specific setup because it's the minimum comminution energy. It might be still arguable, but this is just the minimum comminution energy for compressive load. If you would have impact load, if you would have share load, you would come to completely different results, probably. So
yeah,
I would be cautious stipulating this in absolute figures. It gives another nice results, interesting insights, but I would be cautious in stipulating this in minimum energy.
Yeah, I mean, that's the thing like being a process engineer. So the idea behind is if you are able to somehow find with this methodology, even using compression, that this is the minimum comminution energy using compression, then you can sort of, yeah, in big mills, industrial mills, you already have multiple mechanisms of breakage, compression, impact, also shear. But then you can improve the process towards this line that, well, it is not actually what your plant is consuming. Maybe we can improve that towards. Of course, you're right. Yeah. Thank you.
Just a second question, completely very brief one. Your equipment, your rollers are 100 millimeter wide, your particles are just 3 millimeters inside. So adjusting the roll, it might be quite difficult if you come to close to 2.5 millimeters. So you are aware about the Tulio project in Oulu, University of Oulu in Finland?
Yeah.
The Malcolm is also involved there, and in the Tulio project they also use but a different setup. It's big diameter, but very narrow widths for this roll setup. So you're aware of this project, the Tulio?
You are talking about the Geospora project, the one Simon mentioned.
Yeah, the one.
Yeah, I'm aware of that.
Okay.
The big 2 bicycle wheel sort of stuff, and this one here.
Yeah, big wheels. Okay, thank you.
Yeah, he was my teacher, by the way.
Okay.
Simon.
Yeah.
Yeah.
Okay.
Yes, Marcelo.
Yes, Shujaat, I enjoyed the presentation there. Well, given the time, I'll ask you a very short question.
Sure.
It is, given your experience with this machine, do you see any hope of actually using it as a single particle breakage type of system? Which is, since you could feed very slowly, in principle, you could get the peaks from every single particle, and you could actually, in principle, reach information from a distribution of particles there. You could argue that it's going to take long and you want a quick test,
Yeah.
but you could also drink a coffee and take 10 minutes and come back because it could be fully automated. But of course, the key issue is the resolution. And another, just a comment that I think there's Anne in the audience from Arno's group. I think she's doing a great piece of work as well on this device, but the mini version of it, a very small device in the 100 micron particle range that we have had the opportunity to use. And I think there's going to be some good cross-pollination between the GCC groups on this area as well.
Hi, Anne. I see her now on the screen. Sure.
Do you want to comment on that, Anne?
Yeah.
Yeah, so thank you for your nice presentation. It was really interesting for me what you did, and I think maybe we can talk to each other about the results that we already developed in our time. So
definitely, thank you. Sure.
I think one comment I can make for both Anne and Shujaat, they've inherited equipment that's being modified for something we could purchase. So in fact, out of this project between us, with Anne doing the really fine end and us doing the coarser end, we would hope to come up with one single design that's ideal and would be at different sizes. So you could feed material from the coarsest to the finest through a consistent set of equipment. So one shouldn't be too critical of the designs they've got. They didn't choose them themselves. They're making work what we managed to buy to try and get precise measurements. But I think it's got a lot of promise. Olga's question is really pertinent. I was wondering if anyone else had a comment. I was trying to keep quiet during the conversation.
but Shujaat, just insisting on my question, just quickly on that single particle thing. Do you think each peak could be resolved or not? It's still too far.
I think it's, I don't know. I think I'm not very much. So you said like for each particle breakage, you're sort of interested in finding the corresponding peak for the breakage of each particle.
Correct.
I think it's a bit far. That's where I think.
So maybe it's some more homework for you.
Yeah, why not? I can think about it and I'll get back to you. Maybe I need your insight on that, of course.
So you can measure the peaks. So when you sample at 2000 hertz, you can sample every peak. But we don't believe that's precise enough. It's actually the work, the Geopora that Marcus is doing, that Olga referred to, that's to do the single particles and get like a silk or ultra-fast load cell, a full signal is his intention. So actually we see a good path forward putting the two together.
Yeah.
There must be inertia in the system. So I would try it very slowly and correlate it to normal speed, because the rollers must be flywheels. So they're...
Sorry?
If you only want to measure one particle and this is under normal speed, then you have inertia in the system. So that will filter out the peak. So then you have to consider well, the differential equations for that system. And I think that may be a bit difficult to do. You will get it right as you integrate the energy as you do right now, but monitoring a single particle will be different.
Yeah.
So I had a question. I think it was slide 15. You have the reduction ratios, and it went up to 8. Is that actually the reduction ratio of one particle?
No. It is a reduction ratio of the entire monolayer that I'm feeding in the system.
Because the cumulative reduction ratio.
Yeah, cumulative reduction ratio. Yeah, it's not the one. It's the cumulative one. Yeah, so it starts with the top size, and then I keep reducing it all the way down.
It's after several compressions.
Exactly. Yes. That's right.
Okay. Any other last questions on the future of comminution testing and modeling in the hands of our youth? Maybe with that, thank everyone who joined. We had a really nice attendance again. I hope you enjoyed it. I think Sherry has recorded it if you want to have a review of it or pass it on to some colleagues. Okay. And really pleased to have people joining us. And maybe, Marcelo, you want to close off?
Yeah, there is another last question on the chat. I'm not quite sure. Do you recognize?
So the question is, for small particles, I found that the residence time of the particles on the rows strongly influences the results. Do you have the same phenomena? And that's true. I mean, and I was also sort of commenting that if you reduce the speed for small particles, then what eventually happens is then you have no load time increasing on the rows. Then that will give you, again, sort of misleading results. So I'm now finding like an appropriate feed rate on which I've run my feed, and that should be same for coarser, smaller sizes. And I have already kind of calibrated my feeder on that speed so that there shouldn't be any lag for no load energy, and I see the gap, and then there is no particle falling. So I guess that's what I am doing to eradicate that sort of thing here.
Thank you.
Yeah, welcome.
Okay, Shujaat and everyone. Basically, thanks a lot for the two presenters, and great work from the young guns here. And basically next month, since it's the holiday season, so you won't have an invite for the seminar, so you'll have 1 month off. But early in January, you already have an invitation for seminars that will populate 2021. So in this case, yes, I guess a happy holidays very early on from the GCC group here, I guess. But early 2021, you'll see definitely a nice suite of presentations, certainly by quite a few people from the audience, hopefully. Thanks, fellas.
Sure. Thank you.
Thanks, everyone.
It was great.
Thank you very much.
Thanks for attending.
Bye-bye. Thanks.
Thanks, everyone.